Hello everyone, this is Mr. Math here with another math video. Before this video even starts, I would advise everybody to grab a quick healthy snack, as eating healthy snacks has been shown to improve the performance of mathletes everywhere. So go ahead and pause the video, grab a quick healthy snack, and I'll be back. Alright, welcome back. I hope that was great, and I hope that you're ready to do some math. Now, before we start this video, I would like to give a quick promotion about the Target Red Card. It's either a credit or debit card, and you'll save 5% on all Target purchases, both in-store and online. You'll get free shipping on all qualifying orders on Target.com, and you'll also get exclusive promotions through the Target Cartwheel coupon app, and a 10% coupon for any one Target purchase when you sign up. So visit your local Target, or you can apply online for the Target Red Card. So without any further ado, let's begin with the video. This video it's kind of hard just from the title to know what I'm talking about, but it's kind of just like a weird math problem about the expected distance from the center of a cube given like the angle that it's pointing at, and I'll just get right into the problem here. So we have a hollow cube that has a side length of 2, and in its center is a very small ball with a very short arrow pointing out of it. The ball can be spun in place so that the arrow rotates. If the ball is completely randomly spun, then what is the expected distance of the segment connecting the ball to the side of the cube that is in the same direction as the arrow points? And there's just a couple quick clarifications. So when I say the arrow spins, it spins along a 2D plane, and it is initially pointing perpendicular to the face of the cube. So basically, like when we spin the arrow, it's going to be going like, if this is like a bird's eye view of the cube, the arrow is going to be spinning like this way. It's not going to be like going around in a circle or anything. It's going to be going in a straight line, looking at a face of the cube. So it's kind of hard to picture what I'm talking about. So here's a quick diagram. Basically, we have this cube, and in the very center, the side length is 2, by the way, I think I said. In the very center, there's this little sphere, and it has a very short arrow. For the whole problem, we're just going to assume that the arrow and the sphere have negligible distance, so we're just going to kind of ignore their length. But basically, this arrow is like connected to this ball, and they're all fixed at the center of the cube, and I'm going to kind of, I don't know, whatever, like nudge it or something, and it's going to just start spinning. And when I nudge it, I'm going to hit it with like a random angle, so it could go like this, it could go like this, but it starts pointing like at this, it starts pointing perpendicular to one of the faces. So I'm going to hit it with like a random speed, so nothing's going to be like predetermined. Not like the angle that it's going to take, like it could go like this, or it could go like this, kind of. And from a bird's eye view, you can see that this sphere is directly in the center. So for example, and when I measure the distance, I want to find the expected distance. If I just hit it randomly, what is the expected distance that the arrow will take? Or what's the expected distance from the center to the side where the arrow would hit? So for example, this is the longest possible distance. It goes from the center of the cube to a corner. So this will have a length of square root of 3, because this is like radical 2, this is radical 1, 2 plus 1 is 3, or all of that times 2 and then divided by 2, since it's a length of 2. So yeah, this would be like the longest possible. So like I spun this thing at a random angle, and it just happened to point directly at the corner. It never would point directly there if it was random, but it's pointing directly at the corner. So this would be a length of radical 3. Or it could point just like somewhere over here, and then we would measure the length to this face from where the arrow is pointing. or I could point just like here, I guess. So you can give it a try on your own. I have some hints though. The first one is that the angle is going to be random. So like, well, you can kind of interpret what that means. It's kind of weird, like which angle is going to be random, but like basically like the angle that you initially hit the arrow at is going to be random. So like the trajectory that it takes before it stops, and also like the speed that you hit it at. So you know, it could go like really fast, or you could just like nudge it like barely any. But it's gonna be random, and it's gonna be like a big enough number so that like basically the arrow will just travel a really big angle. So it doesn't really matter like how small it is. Um, Remember that the answer has to be between 1 and square root of 3, since the side length of the cube is 2. The shortest it could be is if it hit like where it started basically, which is the arrow is pointing perpendicular to a face of the cube, and that would be a length of 1. Or I guess if it was like pointing directly to a corner, kind of like a vertex, that would be radical 3. So we should be expecting the length to be somewhere between those two. And the last hint is try to simplify the problem by looking at just one face of the square. So pause it, think about it, give it a try, and I'll show you the solution. Alright, so here's the solution. The first thing I'm going to do is I'm just going to simplify the problem a bunch. So I'm just going to consider the average distance to one face of the cube. Basically, since the reasoning is since the arrow will always point to a face of the cube, it won't ever like point to like an edge or anything, because that has like a probability density of 0. So it's always going to point to a face. So I might as well, and all the faces are the same like distance from the center, and they have the same probability because everything's randomized. So I'm just going to consider one face. It doesn't really matter which one. When I'm visualizing this, I kind of visualize it as like the bottom face, but it doesn't really matter. So yeah, we're just going to be looking at this face. And this dot that I have, like whenever I have a dot like this, it's basically going to represent the center of the cube. And the ray is going to basically represent like the distance. So yeah. This is like another, this is just showing again the longest possible distance is the square root of 3. And this is just kind of a random little distance. Maybe this is like, I don't know, like 1.3 or something, but I just made up that number entirely. But basically, yeah, it's like pointing here. And we're just going to consider one face. Another thing we're going to do is right now, we're just going to consider one axis at a time, and then we can use calculus to consider all possible axes. So what I mean by axis, okay, this diagram I'm going to like show you a lot. This is like a really important diagram to considering the picture, and I'll go over it in detail. Like this doesn't look like a 90-degree angle, but yeah. This blue path is kind of like the path that the arrow would point to. So let's say that I spin it, it could take like this path, it could like this would be like the longest possible path. Well, all the paths are the same length, but this would be the path for this face that would result in the longest average distances. Yeah, that's the right way of saying that. And this would be the shortest average. And so this blue path is just kind of the trajectory of the angle. Okay, what this orange segment is this is just a length of 1. This dot represents the center of the cube. This dot represents the center of the face of one of the cubes. So this is from the center to the face. Since the side length of the cube is 2, so like this right here would be a length of 2. This is obviously half the height kind of, so this is 1. Okay, this is theta. So theta is kind of, you can kind of just like imagine like, well, it wouldn't, you really wouldn't see the cube in a 2D space, so really this wouldn't look like a straight line, the trajectory. Yeah, I don't think so. So basically if we're looking at this from above, like that you could imagine the trajectory, like there would be like another face here, and then it would kind of go off the screen, and there would be another face here, and it would go off the screen. But this angle is random because I'm hitting it at like a random, like when I flick the arrow, it's like a random direction, a random speed. So it's this angle on this one axis is going to be random. And it's kind of hard to draw it in 2 dimensions, but this is a right angle basically, because this orange segment here is perpendicular to the face. So this is a 90-degree angle. And this whole triangle is basically perpendicular to the face. Try to think of it as that way. So like this, try to think of the plane that this triangle lies in. That plane is perpendicular to the plane that this face lies in. I think that's a good way of explaining it. So just by trigonometry here, this black segment here represents the actual distance. So we're trying to find the average length of this black segment for various angles and various axes. So it's equal to secant theta. So we're going to kind of jump right into the calculus here. We'll use the mean value theorem for this because we're doing like expected probabilities and stuff. So we want to consider the average value of secant theta for these values of theta. So the average value of secant theta, we'll employ the mean value theorem here. 1 over b minus a. B minus a are the limits here on our integral secant of theta d theta. And so you can kind of imagine here, theta could be really small. Theta could be 0, in which case the black segment would be the same as the orange segment, and they would both have a length of 1. So yeah, that's our lower limit here is going to be 0 on the integral. A is 0. It's b minus 0, which is just 1 over b. So that's how that simplifies. So now this is the answer to the problem, but it's a little more complicated than this. So the question is, what is b? Well, b is basically the maximum possible value of this angle. But of course, the maximum possible value is really going to depend on the axis that it takes. So, like if this blue line were like, I don't really know how to explain it. It like went from like the midpoint, it connected like the midpoint of both the squares, or like it divided the square into 2 rectangles. If it were that, the blue line, then of course the largest value of theta would be pi over 4, or 45 degrees. I'll just use degrees, and then if we're plugging stuff into the integrals, I'll use radians. And of course the largest value would be, like if the blue was here, then the largest value of theta would be arc cos 1 over root 3. So that's arc cos root 3 over 3. Yeah, which is going to be like a little less than 60 degrees, I guess. But yeah. So obviously we have to use the mean value theorem again to get like an expression for b. So what we're going to end up doing is, I just copied this from before. I'm just going to evaluate this integral. It's a standard integral. You can look up like how you integrate something like this. Because we know secant squared of theta is tangent theta, blah, blah, blah. So basically we'll just plug it in and we'll get this. So now we're going to have to integrate again, because the value of, we're going to be taking an average value for the maximum value of this angle. And we're calling the maximum value of this angle b, just because that's the upper bound of this integral here. And we'll just call d and c. We'll find d and c later. Yeah. Not too complicated. And I'm just going to get rid of the absolute value here for ln, or natural log. So all the angles we'll be working with today are going to be between 0 and pi over 2. So we won't have to worry about secant or tangent being negative. So I'll just get rid of the absolute value, because it's really just redundant at this point. It's just further confusion. So a common mistake that I just want to quickly point out that maybe some people are going to make in the comment section explaining an easier answer to this problem is basically, why don't I just copied this from the earlier slide, why don't we just make c equal to pi over 4, because that's the lowest possible value for if the blue axis were here, and d arc cos root 3 over 3 for if the, root 3 over, if the blue axis were over here. And then we would get this expression, which looks kind of nasty, but we could go online and figure out what this is equal to. The reason why this won't work is because this angle, whenever we move the angle along this axis here, along like the top face of the top edge of the face, so that we can get the value of b for this theta, whenever we do that, we're actually also rotating about the center. So you have to take that into account. And I don't want to go into any more detail, but it's just not going to work. So the angle, we want the angle to vary linearly for like a weight function, for if you're going to add up, if you're going to do the mean value theorem with probabilities. And the positioning angle in the perpendicular frame is, you're adding up the positioning angle in the perpendicular frame, because when you initially spin it, every single, okay, I'm gonna just explain this once really quickly. Every angle in every plane is being spun randomly, essentially, because everything's just random. So the angle is stationary for each plane, and therefore you're adding up a non-stationary angle here, and it's not going to work. Okay, so now that that's clarified, what I'm going to do is I'm actually going to solve this, find the value of b. So we're going to go back to 2 dimensions here. This is the same picture from earlier. Just remember, this is a face of the cube. This is the center of the whole cube. This is the center of the face that I chose. This is a 90-degree angle because this triangle right here that I'm drawing in is essentially perpendicular to this face. The orange is, of course, a length of 1. The blue is just one of the possible trajectories that the arrow could point to. And the black is what we're actually trying to find the average value of, and it's equal to secant of theta, where theta is varying linearly and randomly. So what I'm going to do is forget about this for a moment, forget about the 3 dimensions, we're just going to go back into 2D. So this is the center of the square, and one of the faces of the cube that we're looking at. So of course this has a length of 1 because the side length of the cube was said to be 2, and this is going to be a right angle, and I'm just going to call this angle here omega. So this is just kind of like a bird's eye view of one of the faces. We're only in 2 dimensions once again, and of course just by trigonometry this is equal to secant of omega. So now I'm going to kind of tie the 2 diagrams together here. And so this blue segment here is the same as the blue segment that goes from this. These are both the same point, this and this, because these are both the centers of the faces, and then this is just the center of the cube. So this segment right here, which is I guess exactly half of the blue trajectory segment for this face, is this blue segment over here. So this secant of omega is this blue segment. This one is actually representing the orange one, and the b is just the largest value of theta. So it's the upper bound for the integral. So what we're going to do now is kind of just imagine that this triangle is this triangle that's perpendicular to the face that we're looking at. And b is theta, but the black line lines up at kind of like right on the edge. So theta is like as big as possible without it then going onto the other face, and then theta will start to decrease, of course. But we're only looking at one face. So what we have to, basically this segment right here is going to end up being the black segment, because this secant of theta or this, sorry, secant of omega is this segment right here. This 1 is this one right here. This b is theta if it lines up. So this over here, it would be square root of 1 plus secant square root of omega is going to end up being the black segment. But we don't really need to actually find that for, I guess we could. Maybe that could be another solution of the problem, is to just kind of go around the square and see like what the average value is, and then like integrate a bunch of those squares together. I guess that would get kind of hard with the weight function then if you were to do the probabilities, because of course the smaller squares would be more dense. But anyhow, we have an expression for b in terms of omega, and we know that omega varies randomly and linearly because omega is just in a plane that's perpendicular to the center of the cube. So omega is always going to be random. And this is basically the same as if it were just at the center of the cube. So we don't have to worry about it being non-stationary. So b is equal to arctan of secant of omega. And now we can just put everything together. We just found b is equal to arctan secant omega. So we can now add up the integral here. C and D, I'll get to what these bounds are in just a moment. It's nothing tricky though. We have from earlier ln of secant of b plus secant of, plus tangent of b. This right here, the whole natural log thing, that's just the indefinite integral of secant of b, I guess, db. Over b from earlier, just because we had that 1 over b since we were using the mean value theorem. We're essentially using the mean value theorem twice, so we're going to have a b left over. And that's just from earlier steps. We're continuing that. And this is the d minus c is just from using the mean value theorem. So basically the first time when we used the mean value theorem, when we were just finding the integral of secant of theta originally, that's where the b is from. The d minus c is from when we're doing the mean value theorem right now with the b's and the d's and c's. And this is just from the secant of theta, the ln, and yeah. So basically c is going to equal 0 and d is going to equal pi over 4, because if you look back at the diagram from the previous slide, the 2D diagram, it's an eighth of a square. So that's just 360 over 8 is 45, which is pi over 4. So I'm just plugging in b here. So we're getting secant of arctan of secant of omega plus tangent of arctan of secant of omega all over b, which is arctan of secant of omega, and d omega now from 0 to pi over 4, or definite integral there. And d minus c, c is just 0, so it's just over d. So it's over pi over 4, which is 4 over pi, which I can just take out of the integral because that's a constant. And maybe from pre-calc you learned that the secant of arctan of something is 1 plus, or the square root of 1 plus that something squared. It doesn't really matter since we're just going to be putting all this into like an online calculator anyways, because this is really probably impossible to anti-derive without having like finding the actual area or something. So, and then of course tangent of arctan of something is just that something, because these are inverse functions. And there's not really a nice way of simplifying the arctan of like secant, because it's like the measure of the angle of the ratio, so it just doesn't really simplify that well. And the result, we get this thing. I just stuck it into integral-calculator.com, and I got this result right here. And if you remember earlier, we had this like, this is the right answer by the way, we had this like wrong expression, and it actually turns out to be pretty close, but as we expect, it's a little bit larger because we're not considering like the average of like a norm of a theta that's fixed and in its own plane that doesn't change. It doesn't like rotate. It stays in one plane. So we're going to be like counting the stuff that's like off closer to the vertex more, so it's going to be a little larger. And so yeah, this is the answer. It's a pretty cool, pretty satisfying after like 25 minutes, I think, in recording. We got the answer. So yeah. Just a quick challenge for all you mathletes for homework tonight. Try to write a formula in terms of the length of the cube. So for this problem, we just assume that the length of the cube is 2, and this is like the answer that you get, the 1.145. So maybe try to write a formula in terms of the length of the cube and the various constants. So like this weird constant that we just found, which is like the area under this curve times 4 over pi, which is just weird. But yeah, for the expected distance to the cube's surface. So, or another challenge, I guess you could try this with other shapes like a tetrahedron, or I don't know, maybe try it with a rectangular prism. That could be pretty hard because not all the faces are the same, so you'd have to like consider different faces and then like consider like the chances of getting each face. So yeah, that could be, or a cone. I don't even know how you would approach a cone, but well, actually, that's for another video though. So yeah, have a great night, mathletes.